tried to, this is definitely a robotics focused, sort of in the application space, a bit more robotic focused. There's some teasers in here to like some of the aerospace stuff. My background is in aerospace GNC, but we mostly work on numerical optimization, model prediction control, and a lot of aerospace applications, a lot of robotics applications, other weird applications. So I think we have good overlap with a lot of you folks. I'm really excited about a lot of the conversations we had today. So I'm going to kind of like, my attempt here was to kind of start this out with a bit more of like just an intro to my work over the last few years. And then like, I think the topic of the title here, I'll get into like maybe in the second half of the talk, which I think has been an interesting like recent line of work in the group. Okay, so the intro pitch is I'm a space nerd. This is one of my favorite robots. This thing's been on Mars for like 13 years, and in that time has gone 36 kilometers, which I think is super impressive. Super harsh environment, super challenging. They are doing autonomous driving on Mars, which is incredible, right? Vision, planning, the whole thing. But if you divide these numbers, it works out to about 7.5 meters a day, which is not that impressive, right? It's like going across this room. And I think this picture kind of sums up the reason for this. Does everyone know what this is?
This is like the testing area.
Yeah, it's called the Mars Yard at JPL. It's basically a big sandbox they have out back with, they have like an excavator and a bunch of rocks and whatever. And the rover drives autonomously, but if it runs into any slope above a few degrees, large obstacle, big rock, whatever, it stops, sort of scans its environment and phones home and says, help, I'm stuck. And then the engineers go out in the Mars Yard and they basically reconstruct the environment around the robot. And then they painstakingly, like humans design the trajectory, they go rehearse it a bunch of times, try out all the possible failure scenarios. Once they're really sure it's going to work, they upload the commands to the rover and it drives around the big boulder or whatever along the side. I think the message here is this is not very autonomous. It's a very brittle autonomous system, and it relies heavily on humans in the loop still for its like motion planning and control. And the real kicker here is like, if this happens on a Friday night or the night before Christmas or something, it's stuck for a week. And this is this like multi-billion-dollar platform that's just stuck sitting there waiting for the engineers to come back into work on Monday morning and like go figure it out, right? So it actually has a major impact on the productivity of the mission and all this kind of stuff. So this is the dream, and I love like these videos and kind of looking at the agility with which animals like these are able to traverse even more rugged terrain with no offline planning, right? They kind of can execute these kinds of things. So message is, we want the rovers to be able to do this kind of thing, right? Okay, so this is the part where I kind of like try to indoctrinate you with my view of the world, which is everything is optimization. So I think this is where I'm going to try to do like a really quick kind of tour of like the stuff we've been doing in my lab the last 5 or 6 years. So this is kind of the entry point to all of it for us. Like I'm a controls guy, so we think a lot about this kind of optimal control formulation, and you guys are all very familiar with this, so we don't have to belabor it. But yeah, states, controls. You have a model, which is can be F equals MA, can be learned, can be whatever. Constraints maybe, and then what you want it to do in the form of a cost function. And then generally speaking, in our group, we do a lot of this kind of direct transcription type stuff where we discretize the thing and then throw it at a computer, solve it as a numerical optimization problem. A lot of our work has been on developing fast solvers to do this online. I know a lot of you guys do this stuff too, and you can take this pretty far, right? So obviously we've seen huge successes in this area in the last 10 years or so with like SpaceX landing rockets, and these are just fun videos to watch. So and this was, as you guys, this is like a seminal result, right? Like this was a seminal theoretical result like a little more than 10 years ago, but they figured out how to do this and it had huge impact. And then, our friends at Boston Dynamics also have pushed this technology really, really far and are, I think, some of the best in the world at nonlinear MPC, which is what's doing all this crazy stuff, right? Super, super impressive, right? It's a hybrid system, tons of nonlinear dynamics, super high dimensional, and they're able to solve these problems at hundreds of hertz to do this kind of awesome stuff. Okay, so particularly in our group, we do a lot of work on numerical solvers, and I'll just highlight a couple of recent-ish examples in the last year or two. One is scaling these things down to microcontrollers and like really resource-constrained embedded platforms. This was a paper from ICRA last year, the year before, called Tiny MPC, where we were able to run this is NPC running at about 200 hertz on an ARM chip that I think it's clocked at about 180 megahertz. It's an STM32 on board. We also have this video keeps going, and I think it's chopped for this purpose, but we're able to do constraint handling, dodge obstacles, all kinds of stuff with this, which is pretty cool. And then on the opposite end of the scaling kind of thing, we've also done some work on trying to take advantage of very large scale parallelized compute. That's kind of, we've seen all the development in GPUs for machine learning in the last, 5-10 years. And meanwhile, I think in model-based control, we're really behind in taking advantage of these modern compute platforms. So we were trying to figure out how to take advantage of, basically how do we parallelize effectively on a GPU scale up FPC. This was an effort in that direction, paper called ReLU QP, where we were able to effectively parallelize an MPC problem on a GPU and get really favorable scaling, where we were able to actually run a whole body MPC. So the full body dynamics of Atlas here, which has like a 70 or 80 dimensional state vector and like 35 dimensional input vector. This is running with a horizon of like, 20, 30 time steps at 2 kilohertz. So we're able to do really, really fast whole body control. And the big deal here is that you're getting away now from having to have simplified models and like hierarchical control stacks with low-level torque control, high-level, whatever. You can just throw it all in one big problem and solve it fast enough that you can do everything. And yeah, super competitive with like, CPU-based solvers. Basically, as the problem size grows, this wins by an order of magnitude. Yeah.
And speed up is primarily because you've put on all the matrix vector multiplication.
Exactly. Yeah. So the real trick here is how do you turn everything in the problem into matrix vector multiplication, and because that's what GPUs are good at, right? So there's a bunch of tricks. I'm happy to talk about the detail if anybody wants to or follow up on any of that. The name kind of says it. The tricks in here, we came up with a way of formulating a QP solver as a deep weight-tied ReLU network analytically. So there's no learning. It's you give me the QP and I can transform it and like end up turning the solver into a ReLU network that I can then execute. Like solving the QP ends up looking like inference on a ReLU network. So I can do this now with PyTorch, your favorite toolbox, which is kind of cool. If you're curious about the details, the hint is that one step of ADMM, like OSQP, looks like solve a linear system, which if you pre-factorize is a matrix vector product. And then the prox operator for positive orthant in like ADMM is exactly a ReLU activation, right? It's a clamping operator. So basically one layer of ReLU equals one iteration of ADMM. And we just chain a bunch of them. And if you want 20 iterations, it's 20 layers deep ReLU network. And then you can put it on a GPU. Kind of cool.
It becomes a function, basically.
Yeah. So I mean, it's literally an inference on a ReLU network to solve the QP now, which is kind of cool.
But you do use
the memory, right?
Yeah.
Because we tried something with GPUs way back when, but then the GPUs were really
VRAM.
tiny.
Yeah.
And so if your problem was very small, then you could get a lot of speed up. I guess the one that you're looking right now, they're not like.
Yeah, I mean, this is on a 3090. This was like 2 years ago, I think, when we were actually.
It's still like 16 gigabytes.
Yeah, so what's going on here, the VRAM situation is that each layer here is one of the key tricks is that this is a weight-tied network. So most of the iterations look the same. So we only have to store one of those matrices for many layers, right? So we're storing about 5 matrices in here.
Okay.
And that comes down to, in ADMM, when you crank the penalty parameter, that's a new matrix.
Yep.
So we pre-compute offline about 5 of those on the scale. And then online, we stack them however we need to. And it's about 20 layers, but it's only about 5 different matrices. And we're pushing the VRAM limits for problems like this. This is a big problem, though. This is like 100 dimensions per time step, between state and input, and then about 20 time steps. So it's tens of thousands of decision variables. So we're solving some pretty big, anyway, it's fun. Okay, cool. So yeah, we do also a bunch of work in state estimation, which looks exactly the same as trajectory optimization if you're twisted like me. Model the robot. Now your control input is your noise. Right now you have a least squares loss, so it's a special case of trajectory optimization. And in recent, last few years, I've talked to a few of you guys about this. We've been doing a whole bunch of work on multiple spacecraft kind of relative navigation type stuff. And this was a mission we flew last year called Pi 4, which is 4 of these CubeSats that you see here. They have crosslink, S-band crosslink radios, and they can do time of flight ranging measurements with about 1 meter precision. And we were able to take those range measurements and uniquely determine their relative orbits. And then by making one of these arbitrarily a so-called anchor node where it knows its absolute orbit, you can then bootstrap absolute positions for everyone in the swarm. The trick here is that you can imagine if you only have range measurements, you can arbitrarily translate and rotate the swarm and it doesn't change the measurements. So there's some observability issues. The trick is that we take about a full orbit's worth of data and we use a very high fidelity dynamics model that includes high order gravity terms. So lots of like non-spherical perturbations and also drag model. And for the drag model, we're actually estimating out like atmospheric density terms and things like this. So it's very high fidelity dynamics model. And by having those additional terms, we sort of break the symmetries in the problem. And so given enough time history of data, it becomes observable. But you need actually like an hour's worth of data plus the high fidelity dynamics model to make it observable. So it's quite a hard problem. It's like very weakly observable. But in the end, we got the results you see here on orbit. The green dot is the so-called anchor node. And then the red lines are the range measurements. And the blue curve is the fit relative orbit. We're able to get this down to a couple of meters, 1 sigma relative position accuracy. It's pretty good. Okay, and then like kind of the other thing that I'll try to convince you of now is we've done also a lot of work in physics simulation, where we treat this as optimization. Who knows what this is?
Action.
Yeah, this is Hamilton's principle, right? Least action. And the cool thing about this, and for those who haven't seen this or haven't seen this since college, you know, and it's fuzzy, the L in here is the Lagrangian, the Q is your pose trajectory. This is like kinetic minus potential energy. And if you kind of squint to this for a second, this is the integral of this Lagrangian along a trajectory. So if I say the Lagrangian is a stage cost, and if I make Q X and Q dot U, this is exactly a trajectory optimization problem. It's sort of, you know, the trajectory optimization problem that nature solves in some sense. And there's an exact equivalence actually. That the exact equivalence is called the Hamilton-Pontryagin principle. And if anyone wants to talk about this at Nerd Out, I'd be happy to. But you can pose physics as trajectory optimization as well, which is kind of cool. Why would you do this? Because so you can do this. Then we can play our usual games of discretizing, you know, and solve it numerically, just like we would any other trajectory optimization problem. The reason you might do this as opposed to your standard rigid body dynamic stuff is I can now include inequality constraints in this problem. This is super useful for handling non-smooth dynamics like impacts and friction that show up in robotics all the time with manipulation problems. This is kind of a quick example of this, where this phi greater than equals 0 thing is sort of the height of this brick above the table. And it says the brick can't go through the table. The gradient of that now becomes the normal vector, and the Lagrange multiplier becomes the normal force, and it's all really clean. And you don't have to write down like weird approximate soft spring damper contact models or anything. You don't have to worry about stiff ODEs. It all just works. It's normal constrained optimization now, which is kind of cool. Similarly, Coulomb friction, which is also a mess, you can formulate this way. It's called the maximum dissipation principle. It's another nice convex optimization problem it turns out. Where it says that Coulomb friction is the force that sucks out the most kinetic energy instantaneously at every time step, subject to lying in this friction cone constraint, which is like, you know, friction is, you know, less than equal to some friction coefficient mu times the normal force. It's like almost the thing we learned in high school. And then the last one I'll mention, this is kind of work out of our lab in the last couple of years that I really actually like. And this video is kind of messed up, sorry. Collision checking actually is also another one of these problems that's kind of nasty. The classical methods for doing this that are widely used in computer graphics are called GJK, and there's many similar ones that effectively check vertices and edges of polytopes to try to figure out closest points and intersections and things like this. This is fine, it works really well, it works in game engines. The problem is that it's not differentiable, and it's kind of got this discrete search flavor to it. So what we do here instead is we're able to pose this as a convex optimization problem if the shapes are convex. And there's a whole little side conversation to have about that. The way it works is you take two convex objects and you search for the minimum in uniform scaling or like inflation factor alpha, such that the two shapes just touch at a point. And so this is really cool because number one, it's always well posed. It always has a solution. basically if they're actually in contact, alpha equals 1. If they're in penetration, if they're overlapping, alpha is less than 1. You have to shrink them back, right, to get to a point. And then if alpha is positive, it means there's separation between them and they're not in contact, right? So this subsumes every case. You don't need to special case anything, and we can cleanly diff this and get nice gradients, which is kind of cool. Yeah. Okay, so this is like a bunch of stuff we've been doing in the last few years regarding optimization solvers, treating everything as optimization. And then a lot of the work has focused on this question, right? How do we put all these pieces together? So I showed you, we can make friction into an optimization problem, collision checking into an optimization problem, dynamics into an optimization problem, estimation, control, right? These are all individually optimization problems, but now to do anything, if I care about controlling a robot, I have to somehow hook all these things together. And so now what you get are a whole bunch of coupled optimization problems. They're nested in weird ways, and I have to somehow jointly solve them. So how do we do that? So we went deep down the rabbit hole on this sort of what I called composable optimization, this idea of how do I hook together multiple problems and sort of solve them, and what does the solution look like? That's some weird notion of equilibrium. So the way we do it in practice is if you zoom in on, say, one of these blocks, and inside that block, I have, let's say, we'll now deal with this slightly simplified problem where it's just minimize objective subject to, say, one inequality constraint. I'm gonna, and so to take an example, let's zoom in on like maybe the friction problem that we just looked at. So then this is the friction cone. And notice here I've got two variables, x and y, but I'm only minimizing with respect to x. So we'll call x the decision variable, right? And y is a parameter. So it's a variable. The solution depends on y. So in this case, that might be like the normal force, right? Which I'm optimizing in some other block. So the solution here depends on that, but I'm not optimizing with respect to that, right? So that's kind of the setup. The gist of what we do is we take this, we write down an interior point solver for this problem, which basically, like, wave your hands a bit, amounts to taking the constraint and sticking it inside a log and putting it in the cost function. Lots of details. And that looks kind of like this, right? So the log blows up as you get to the constraint boundary. And there's this fudge factor in front, that row that we call a central path parameter or barrier parameter. And so that smooths out the constraint. It makes it nice and differentiable. And as I crank rho down, I approach the sort of brick wall, right? Okay, so that's the idea. And this is, very classical optimization stuff. And we know how to solve these problems. We know how to write the solvers for these. It's in textbooks, right? Like, we know how to do this stuff. Okay, so now that I've done this, I can write down the optimality conditions for this guy, the KKT conditions, which amounts to this sort of algebraic, thing equals 0 kind of condition. And I can also use the implicit function theorem to compute dx dy. So, and in particular, maybe this isn't obvious, but the fact that I've done this interior point log barrier trick such that everything's smooth and differentiable is what lets me do this implicit function theorem thing. So the gradients are always well-defined. I can always compute them. I needed them anyway to solve the optimization problem. So they're kind of already floating around. And this implicit function theorem trick lets me take those Jacobians that I've already computed inside my Newton solver and kind of massage them around and get the gradient that I want. Okay, so now that I've got all this, I can take this block that's some weird inequality constrained optimization problem, and I can essentially treat it as just a function x of y that I can query for its value, and I can query it for its derivative dx dy. So now this thing is some weird inequality constrained optimization problem. I don't have to care about that anymore. All I have to care about is that I can basically treat it like it's any other function, and I can use it now in an objective, in a constraint, in another optimization problem. So now the big idea is I have all these blocks. Now I can make them, with this trick, I can make them all just look like functions, and I can combine them arbitrarily and kind of nest them and build weird composable things with all of these things, right? Okay, so what do we do with this? We built a simulator with this. We kind of put together a bunch of that stuff. We've done what's called contact implicit MPC with this, where we've taken all of this and the control problem at the top and played a lot of tricks to get it to run fast. So this is like a simulation example. We made it go fast enough to put it on hardware. Not super impressive given things you've seen in the last few years. This is a few years ago. We've dabbled in some manipulation stuff. This is kind of a cool thing where we directly use a point cloud in the dynamic simulator. So like the vision here is you could take raw point cloud data from a sensor and directly suck that into an NPC scheme where you can simulate interactions online using point cloud stuff. We recently had a really fun project on large deployable space structures. And the video that you see on the left there is actually on a 0G flight we did in the spring, where we kind of looked at these large scissor mechanisms. And there's all kinds of weird stuff that happens in these things when you have joint clearances, when you have like joint slop, what do they call this? Like sort of manufacturing tolerances where there's little gaps everywhere. It doesn't behave the way you expect. And so what we're able to do is take motion capture or even just monocular video data from these things and track these things and back out the tolerances. We can back out from video data the manufacturing tolerances and the joint reaction forces because we're able to use this simulation tool that can sort of account for all this stuff. Kind of fun. And then recently we've done a ton of work on also using the same set of ideas, it turns out. We can handle fluid structure interactions. So classically in computational fluid dynamics, you'd use something called the immerse boundary method for this. But it turns out the interaction between the fluid and the robot and the boundary conditions at the interface, you can formulate those in almost exactly the same way as impacts in mechanics. It's an inequality constraint that says the fluid can't penetrate inside the body. And the Lagrange multipliers are the pressure forces, and it's super clean and super nice. We've actually used the same, basically same optimization tooling and same setup that we use for the impact dynamics to handle fluid structure interactions. So these are some preliminary results here. We've actually got some really nice new results with really good sim to real matching with a slightly different robot, a more like eel-like, snake-like robot. And the thing on the right is actually showing the famous dead fish experiment, where the dead trout swims upstream, if you guys have seen this before, by exploiting vortex interactions. This is a simulation of that. Anyway, okay, so that's some. And then the last one maybe I'll mention is it turns out that this setup where we've got all these coupled optimization problems that are kind of combined and nested in weird ways, it turns out that the closest thing to this in the literature is a Nash equilibrium. So-called generalized Nash equilibrium. And this idea kind of is more general, though, than these game theoretic equilibrium concepts. So you can actually model things like Stackelberg games, Nash games, min-max sort of robust control type, setups in this framework as well. And so there's a couple examples of this. We've also done a little bit of this with like multiplayer games modeling driving scenarios. And this is an example of like, a classic kind of min-max robust control thing where we've kind of solved it using this framework. So it's pretty general, and it again includes a lot of these other things that we know about in a pretty clean, like computational framework, right? Okay, so this is a bunch of weird stuff that we've done in the last few years that like, I think it's pretty and kind of cool and whatever, but I think there's a good argument to be made that's really complicated, and getting into it's quite hard. Like getting students spun up on this is pretty difficult, and like other people who've tried to implement this stuff, have struggled. It's pretty hard. It's pretty gnarly. The math is hard, and the solver implementations are quite complicated, right? It's hard to do this. So I think a thing that's happened in the last couple of years, as I've been doing this for 5 or 6 years, I've had now the opportunity in the last year or so to step back a bit and sort of maybe question my initial assumptions and ask, is this all really that hard, right? Did I really need all this insane kind of coupled, optimization stuff, these really complicated models to do this? And I think the answer to that is clearly no. And in the last few years, there have been a few papers that have really kind of inspired me and made me rethink some of these things. So this is my personal journey I'm sharing with you now. It's like group therapy. So one of the first papers that really, I think, along these lines that's interesting is this one from Ben Recht. You folks remember this? It's like a 2018 paper where they basically showed, there's all this kind of like crazy stuff going on in reinforcement learning with these really complicated algorithms, like estimating, advantage functions, value functions, and, neural network policies. And what this paper showed.
It's not you, it's just the system.
Okay.
It's gonna come back eventually.
All right. Well, while we wait, what this paper showed is they basically matched state-of-the-art reinforcement learning results with linear policies and the dumbest possible gradient-free random search optimization algorithms. So that, and these are examples, right? So really, really simple algorithm, really, really simple policy approximation, policy, sort of parameterization, linear feedback, and you got basically matched state of the art results in all these like OpenAI gym kind of context, right? Kind of interesting. Another example, this one was from 2020, I think, from Russ Tedrick's group, where they were doing like this kind of object pile manipulation. So this is like chopped vegetables, and they were using vision and trying to like manipulate these piles into nice, neat little piles. And they showed here they were using, they used linear models to do all of this in pixel space. So it's like really, really simple, ideas, doing something that people had been using really complex, neural network models to do the prediction part of this, right?
Now, what the problem is that if you make like these simple things work, that you cannot write any MERL papers about it afterwards, because you show that simple works. So why do I have to write another 20 papers about it?
Maybe that's true. Well, I think so. Here's my take on this. I think to do the simple thing, you actually have to be really clever. I think that's my takeaway. But these were just things I looked at that I liked, right? That were kind of inspiring. So this was one, and then this was one also. This was actually one of my students, Taylor Howell, was the first author on this. He did this as an intern over a summer. It was a summer project where they did what they call predictive sampling, which is essentially MPPI, if you guys are familiar, but it's the dumbest possible optimization algorithm. You basically you randomly sample control trajectory or short horizon. You maybe sample a few thousand, you roll them all out and you pick the best one. You run that and you do MPC based on this. You run the first action, then you sample around that last best one. Take a Gaussian with the mean centered on that last best one, do the same thing, repeat, right? And they showed really good results in simulation. So this is an example of this, like crazy stuff, right? This is in Mojoko, and we can argue about, physics accuracy and everything else. But the fact that they're getting these really, really kind of amazing dynamic behaviors to come out of the dumbest possible algorithm, right? I think is pretty compelling. So we took this and we started trying to put this stuff on hardware from here, right? That was the takeaway. That's kind of the stepping off point. So here's a couple of quick examples. This is actually where we started. This is actually running vanilla iterative LQR, or differential dynamic programming, on the Mojoko soft contact model. So it's really, it's the textbook algorithm with no secret sauce. There's no constraint handling, there's nothing, right? And I'm getting these like pretty, like walking just works. I can drag the reference around. I can do this like handstand craziness. So highly dynamic, like really impressive results. Again, something that like I learned, as an undergrad and like spent years on, and like now that's just doing these amazing things. And like, why didn't we do this 10 years ago, right? Emo wrote these papers like more than 10 years ago. Why didn't it happen then? I think it's literally just that computers got faster. And we know about GPUs and all that in the last few years, but CPUs also have gotten much, much faster. And this demo 5 years ago wasn't fast enough to do in real time on hardware, on like the state of the art processors.
This is another example that simple sometimes is more robust.
Yeah.
Because the $5,000 projector didn't have these issues before. And this $50,000 system does.
Yeah. We do website. We try to plug in.
No worries. Okay.
Let's see if maybe that works.
No. So yeah, this is kind of cool. Okay, so this was the iterative LQR. Then this is kind of the predictive sampling idea. I just described this. Sorry, the slides are a little out of order. Randomly sample, pick the best action, run the first time step, resample around that, repeat, right? So it's MPC, but the dumbest possible optimization out, right? It's single, it's shooting, yeah.
That was borderline what that goat was doing at the start, right?
You could argue, yeah.
It's not the.
I mean, it's hard to say what that is, right?
Right.
Like there's learning going on there. There's some amount of.
Here there is no name, you just shoot.
This is the dumbest thing ever.
Basically, it's forward simulation to the input instead of even doing like RRT where you do.
It's single shooting.
The point and then you reconstruct.
It's literally single shooting,
Exactly.
but gradient free. And you're not even doing anything smart with the sample. You're literally just picking the lowest cost sample and running that one.
Which points me out to another thing that I think the point is to give him a cool acronym, because if you call it like just I'm simulating the system, nobody will use it. If you call it MPPI, maybe the name is kind of appealing.
But that's the thing about this. Okay, the MPPI, they dressed it up a lot. I mean, I like this work, but it was dressed up in a lot of like stochastic optimization and theory. And this is, the dumbest possible thing, and it works great.
Yep.
In fact, this actually performs comparable or better than MPPI with sort of more sophisticated resampling strategies. This just works. And like, this is, again, there's nothing fancy. It's literally sampling from a uniform Gaussian and just setting the mean at the last best sample. So this is the full stack. There's a few tricks in the implementation details, mainly that, this does suffer from recursive dimensionality where, higher dimensional space, getting good coverage from the sampling is hard. So what we do here is we try to reduce the dimensionality of the sample space, and we also try to the other thing you can get out of this is very jerky control signals, right? So to alleviate those issues, what we do here is sample over a spline. So we parameterize the control trajectory over some horizon, a couple seconds, second or two, as a cubic spline. We sample the control points of the spline, and then that's how we generate our controls. Roll that out. So the search space it's whole body control. So it's like all the actuators, right? The whole U vector parameterized by the spline. So it's 4 control points per U dimension. So we do this. We're actually able to do that with a few dozen samples at about 100 hertz. And then underneath this, we take the joint targets from this, we extract them, and then we pass that off to the low-level PD controller on the robot. The reason we do this actually, instead of direct torque control, it turns out the interface, the software interface on the Unitree robots for doing direct torque control is bad and has horrible latency, and their low-level PD is much better. So that's the only reason we do this. And that runs at a few hundred hertz. We've got an EKF doing really simple state estimation from mocap, and that's basically it. So here's a few examples of this on hardware. This is, it looks kind of stupid. It's a little jerky still, but the really compelling thing about this is it does not care about contact at all. Like, you just do rollouts. There's no derivatives. I don't care about any of the non-smooth badness. I just sample over it. And it's pretty robust. It's also, the other cool thing about this is it's accounting for, normally when we do this kind of MPC stuff, we're only accounting for point contacts with the feet, right? This is using the full body collision model in MuJoCo that it can simulate. So it's actually accounting for contacts with the entire body. So when it like bounces the torso off the obstacle, that's in the simulator. And in principle, it can exploit that kind of thing. So this is just walking around. This is doing some kind of very crappy manipulation where we're trying to push this box into a target. You'll see in a second, there's like a point on the floor that we aim for. And the cool thing here is, again, this is like the cost or function here is literally just a penalty on the box being on the X. That's it. All the rest of this just flows out of this, again, really, really dumb and simple optimization. So figuring out, that it can push the object with the head of the robot, like this all just comes out of the sampling. Like, we're not specifying anything like this at all. Okay, so that's like the dumbest possible optimization algorithm with fast simulation. Another thing we've gotten into, which I really like, is how far can we push linear models? So here we go back to that optimal control problem where we've got a linear dynamics model and a quadratic cost. And here when I say linear, I mean LTI. This is a single linear time invariant model for the whole body dynamics of the robot. And frankly, this really surprised me. Like, when I first saw the Cheetah MPC work, it's really cool. It looks awesome. They did a lot of model simplification when it's a single rigid body model, and they have all this complicated stuff with like low-level swing leg control, and it's kind of broken up in a bunch of ways. And I always kind of felt like, why don't I just linearize the whole body dynamics of the robot, like use that, like why not? So we finally did this, and it works great, like surprisingly well. So yeah, this is an LTI model. The insight here, and this is kind of a classic kick the robot demo. The insight is that if you're doing this kind of walking, if I take the whole robot and I take it in some nominal standing pose and I just linearize everything there, if you look at the motion here, the joint angles are not that big, right? The variation in joint angles, maybe plus or minus 10 or 15 degrees tops in sort of normal walking, you're well within a small angle approximation. So a single linear model works great for that. Similarly down here, this is actually maybe pushing it a bit harder. Here we specify like a goal pose. So it starts over here. All of this is a single QP based, kind of LTI based thing. It's linearized about that standing. So standing up, walking to this target, everything is one linear model. There's a little bit of trickery going on in like the handling the large yaw angle. We do some stuff that I stole from the aerospace world where we do kind of this. We write the dynamics and like the errors down in the body frame, the sort of invariant, and you can get away with now large angle stuff with a single linear model quite well. So, but yeah, with that trick, like this works again for almost anything you want to do that's sort of not, acrobatics and backflips. You can get away with an LTI model in a surprising array of.
Sorry, quick question.
Yeah.
Because the cheat of the goal was to get it to around 25 miles per hour. And so there, I guess the angles become a little bit bigger.
Not really, and they're using the single rigid body model.
Okay.
It's linearized, right? So
you think
they're
this is
taking the torso. There's an interesting, story about like code design and control and
Yeah.
whatever. They made the legs really lightweight, low inertia, and so most of the inertia is in the body. They use a single rigid body model that's just the body. They linearize it about like Euler angles, and then all of the leg stuff is all like inverse dynamics, inverse kinematics with pre-specified,
okay.
foot trajectories and all this stuff. So it's very simplified. I would argue there's less simplification here than in Cheetah. Like this is capturing more.
Because I don't remember where, but I saw the words with friction cones and so on.
Yeah.
At least you will need the conic.
So we have that in here. Like
Okay.
we actually have there what they do is they linearize that friction cone and make it a pyramid. So it's a bunch of linear
Okay.
constraints and it's a QP.
Yeah.
So we have all of that in here actually. It's
Okay.
exactly the same as they do.
Okay, because then it allows you to control basically stability.
Yeah. So here we have, so the gist there is instantaneously, right? You have like 2 points of contact. So it's under actuating all
Yeah.
over. But if you have a horizon that's a full gate cycle,
Yeah.
over a gate cycle, it becomes
Then you recover
controllable, blah, blah, blah.
controllability by
So yeah, that stuff is all the same. But yeah, I don't know, kind of interesting that like, again, LTI model on something you think is very, and yeah. The next video is cool. So I don't want to, maybe we'll try this.
Yeah.
So this is on a legged robot, and we're familiar with these things, being sort of, controlling these with QPs maybe. But I think maybe more cool is, recently all this humanoid stuff. We've been, like there was this kind of idea in the community that, humanoids are way harder to control than quadrupeds. They have to balance, blah, blah, blah. This is an IHMC in Florida. This is an old hydraulic humanoid that actually has like pretty terrible hydraulic actuators with a lot of stiction and weird nonlinear stuff going on. And same approach, we take the robot, we linearize it about this nominal standing pose, and we just make it walk with the same kind of stuff. So it's LTI model. So like a lot of the stuff that we've seen, I showed the Boston Dynamics video earlier on, like that's really sophisticated nonlinear MPC. Like how much nonlinearity do you really
You don't
need?
even need control barrier functions here.
You do not. No. I mean, this is just a QP. It's a really, really simple QP. And going back to that ReLU QP stuff, because it's an LTI model, I can pre-compute all the matrix factorizations here, and I can do outrageously fast online feedback. So if you kind of look at it from that perspective, I could start adding in pretty sophisticated actuator models. As long as I add linearity here, I can make the state and input dimension huge here, because if I can use that approach, and I can still solve it at like a kilohertz. So I don't know, that's kind of interesting. And then the last one I'll kind of highlight here. We also kind of have been like, I've been interested in like, looking at all these like pixels to torques kind of things, more recently behavior cloning kind of things, where you've got really high dimensional, mostly vision inputs. Like there's been this kind of notion that you need deep learning to do this, right? And meanwhile, I've looked at some of these things and thought, okay, like maybe a few years ago, you saw these results where they did pixels to torques control the earlier stuff on like cart poles. And I look at this and I say, okay, it's a cart pole. I can linearize this locally about the upright, and write a linear model down. There's nothing like, if I had a deep neural network policy that could control this thing, I have to be able to linearize that neural network policy, and it like about some nominal upright equilibrium. Like the world is still round, that has to work. I have to be able to do this. So it's like, if that's true, like I should be able to build a linear feedback policy from scratch that sort of does the pixels to torques thing. And so we did this, we built this kind of setup. We have like a nice webcam kind of little thing. And this is kind of the gist of how it looked. We we did like almost like behavior cloning kind of setup, like with a student teacher thing where we have a join encoder, we have a nominal setup with a join encoder, so we know the state, and we do LQR and we can balance the cart pull. Then we stick a camera on it and we collect a bunch of data using the camera. And then what we do is train the student policy, which is pixels to torques, right? Only has the camera, doesn't have the encoder data. But here we're assuming it's linear. So the student policy is basically a classical linear observer, linear feedback controller, right? So it's a Leuenberger observer. So my learning problem now is linear least squares. It is, but the inputs are, the Ys are images, right? So it's, I vectorize the pixels and stack it up. But it's, yeah, it's super clean. It's linearly squares. It's all really nice. So here's this thing running. And I'll like say a few what I think are kind of interesting things about this. So you see here, we've got this, you know, people in the learning community made this big deal about, oh, it's robust to occlusions, right? And so here we're showing, you know, okay, I'm putting my hand in front of the camera, occluding, and it's super robust and it works. The interesting thing here is if I stare at what I get out of this, I have my Leuenberger observer. This is a gain matrix that sort of you multiply by an image and it spits out a state update, right? Okay, so if I look at that gain matrix in my Leuenberger observer that I've learned, or learned meaning linearly squares, right? The rows of that thing are taking dot products with the image, right? So the first row takes a dot product with the image and spits out an update on the cart position, say, right? The next row takes a dot product with the image and spits out an update on the pole angle, right? And when we solved this least squares problem, we regularized it, which we kind of always do. And we, in particular here, we did the lasso trick. So it's an L1 regularized least squares problem. What that does is encourage most of the matrix to be zeros, right? Okay, so if you think about this for a second, so you can take the rows of that Leuenberger observer matrix and you can visualize them as images, right? So if you do this, if you look at the image that's updating the cart position, it's all zeros except for a strip at the bottom around where the cart is. And if you look at the next row, which is updating the pole angle, it's all zeros except for a narrow strip near the top of the pole and the bottom of the pole, and they're kind of opposite signs. So it's basically doing like a cross product-y thing to extract the angle. So very intuitively, you see that this thing is naturally robust to occlusions because most of the gain matrix is zero. It only cares about the specific areas where there's information to be had, right? And it kind of just all falls out. So I don't know, that's kind of cool. And the thing I really like about this, I think, and we're kind of trying to get more into this line of work, is I think, you know, these deep learning approaches are really powerful. There's a lot of really good stuff in there. There's obviously new capabilities that we're gaining thanks to these things. But I think everything is still locally linear, right? I can still zoom in and look at these things from a linear systems perspective. And I think there's still a lot to be gained from that. I think we can learn things about how these things are working under the hood, about the structure of these things. So I think, like, I would argue that like our classical linear systems tools are still very much applicable to these new settings, and we should be enthusiastically sort of like bringing these tools to bear on these new tools, like these new things, right? We shouldn't give up on eigenvalues and all the stuff we know. And our stability analysis tools, I think they still very much apply. Okay, with that, I'll sort of shut up and just leave you with some parting thoughts. First one, yeah, I love, these are 3 quotes, right? Make things as simple as possible, but no simpler. I think this is sort of the virtue of simplicity thing. Like a lot of these newer control approaches are, you can get away with really simple stuff, right? The next one is a classic from Art Bryson, be wise, linearize. And I think what I was just saying, I think there's still a lot we can learn from linear models, linear systems theory, even in the context of like large behavior models, diffusion, et cetera. And I was talking to some of you guys earlier today about some of these ideas. And the last one, yeah, I think still for me, and we also talked about this earlier today, I think modeling and simulation is still a crucial bottleneck for robotics. And in the context of all this data-driven stuff we're seeing now, like if you want to build control policies from, say, monocular videos or whatever, you need simulation. Like there's too many missing pieces of the puzzle in there. Like you don't have contact forces and things like this. You need to fill in the gaps with simulation, right? So I think we're still, and there's still a lot of work to do in that space. Like we're really bad at soft bodies. We're still pretty bad at patched contexts and dexterous manipulation. So I think there's still a real need for that kind of stuff. These are kind of, you know, I don't know what we're doing at least, because that's what I know how to do. Lastly, yeah, these are all my students who do all the real work, who did all the stuff I just showed you. These guys are awesome. A couple of these guys have graduated recently. But I think, these guys, I think a bunch of these guys will be looking for internships and things in the next couple of years, and we can talk about that too. And with that, I will leave you with my contact info. I'm now up the street, so I hope we can keep chatting, and thanks for having me.
So your pixels to torques thing, do you think that, like, how far can you push that? Can you go pixels to full self-driving?
Not with a linear model. Oh, well, okay, so on a track in a, I wouldn't do this in the wild, but I absolutely think you could drive it. Yeah.
So what's happening in the wild that breaks the assumptions that you?
I think it's really the perception of it that's hard, right? Like this is a very benign, like we got away with low big depth grayscale images here because we engineered, we put it in a black background with a white, foreground thing. We made the vision problem really easy, but I think the perception problem is really hard. If you go out in the wild and there's like, crazy lighting and like just the infinite variety of the real world, you're not going to get away with a single Lumenberger observer, right? It's too hard. So I mean, I think that, but yeah, I think like the driving the car problem, I think you can absolutely turn into convex MPC, right? Yeah. That said, yeah, I think there is an interesting in between here, which we've actually dabbled in. There's some follow-up work on that carpool problem. We actually did the full swing up version of this as well. And the way we did that was we took this, we did like a sort of a Kupin lifting where we hand engineered a couple dozen features, nonlinear features, in such a way that it's still linear in the feature space, and then repeated the same thing. Basically, we added a few like Fourier features of like a few sines and cosines of the angles and stuff, and stacked that up, and then repeated the whole thing, exactly the same exercise, and it works in the nonlinear. It generalizes then to like the full, 360-degree full angle scenario as well. I don't think it's super surprising. Yeah.
When you mentioned these like game theoretic approaches and looking at like min-max problems, could you share a bit about how big you're able to tackle those, and then also a bit about like how you solve them? Because I do bi-level optimization in my thesis work, so I'm curious.
Cool, super into this stuff. So yeah, we dug into this quite a bit for a while. Like basically, okay, the backstory here is I was doing all this contact stuff. I got to Stanford, I met Max Schwager, who was doing a bunch of like multi-agent game theoretic stuff. And I had a conversation with him where I was like, oh wait, like the thing I'm doing is one of your games. And so we teamed up where we built numerical solvers for a bunch of sort of multi-agent game stuff he was doing. Mostly, it was funded by TRI at the time. It was mostly looking at like driving scenarios with humans and whatever. So yeah, there's lots to say about this. I would say like we were able to do this. We wrote a couple of papers, one called Owl Games, what's it called, Lucid Games, where we did like online sort of like objective function estimation for the other players, like online learning, adaptive kind of version of it. But we were able to do this with like a half dozen other vehicles and the ego vehicle at real-time rates, like 30, 40 hertz. So it's like we can solve large enough problem instances for it to be interesting in an online driving context, if that is good for calibration. And those were like, I mean, it's like doing nonlinear MPC, and it was a little sketchy, but like we were able to, solve the problems relatively reliably, quickly enough to kind of do the thing. But yeah, this is a deep rabbit hole. I'm sure.
Yeah. Do you do like the dual, like take inner duals to try and get it to single level, or do you do other things?
So there's a bunch of ways of thinking about this problem, right? So one way of doing it is you can basically take the inner min sort of write down KKT conditions and nest them, right?
Yeah.
And then you get like an MPEC or mathematical program with complementarity. We don't do that. So if you go into the numerical, I started out like looking at things like this.
Yeah. It scales horribly.
Well, it's not that it scales bad. Like in terms of dimension, it doesn't scale.
Right.
The problem is that setup, complementarity constraints in particular, when you have inequalities, right? They violate LICQ, which if you know numerical optimization, this is like regularity assumptions you need on the constraints. They always violate them, right? So the way we get around this, and I think the right way of thinking about this is like that MPEC setup or MPCC setup is just a bad it's a bad problem class. Like you're thinking about it the wrong way. What you're doing there specifically is you're throwing out structure. Like the real problem is really a coupled multi-optimization. Like it's this composable optimization picture, I think that is the right way to think about it. So like I have a bunch of optimization problems that are coupled. They're cross-coupled through various variables, right? That I think is the right picture. When I go to that MPEG setup, I'm throwing out that structure. I'm taking all of these other problems, I'm writing down their optimality conditions and just stacking them. And so I'm like going to the single level problem, but it's a mess. And I think the key insight you're losing there is I never solve an optimization problem numerically by directly attacking the KKT conditions ever, because they're terrible. What I do, I can do active set, I can do ADMM, augmented Lagrangian, interior points. There's a million things, but all of them are basically approximating the KKT conditions in some way, right? Interior point, you smooth the KKT conditions. ADMM, you split, right? Augmented Lagrangian, you put them in a penalty. Like they're all doing something to sort of massage or relax the KKT conditions. And that's because on their own, they're terrible. So by taking them and treating those algebraic constraints, what are you doing? Like it's on its face, it's a terrible idea, right? So the key insight here is you treat them as separate problems. You write down a good solver for each subproblem, and then you hook the solvers together.
Right.
That's the insight. So what we do here is basically we take all those blocks, we take each block and write down an interior point method for the block. And then we wire the interior point solvers together. And like, that's the key insight is that like, you want to do it at the solver level, not at the KKT level.
Okay, thank you.
Long rant. There's other weird stuff to get into the game theory stuff. I mean, the other thing there is that like the notion of equilibria there is like super weird.
Well, yeah, because
There's a long conversation to have about that, which we played around with some stuff there too. It's kind of cool. You get in all these situations where equilibria are and not only are they non-unique, they're not even isolated points.
Right.
Subspaces of solutions that are all connected. And you can like, once you get in there, there's like a manifold you can trace out with continuation methods to like, weird. Yeah.
Nice talk, Zach. For the differentiable part, like in the same line, are there any conditions that you prefer to have these blocks have so that you can come up with this del x by del y and
Yes, absolutely. Yeah.
Oh, could you go a bit?
Yeah. So I mean, it turns out most of this is another reason why I hate the MPEG thing, and I think this is the right way to think about it. Most of the blocks are convex that I wrote down. So if the block's convex, your life is great. Like interior point methods always work. Right. So the hooking them together is hard, but on an individual level, if the subproblem is convex in that block, then the KKT conditions are necessary and sufficient, and I can always diff them, right? Like as long as the modulo like feasibility, blah blah blah, but as long as you have a nice convex problem in there, I can always do it. Like I can always write down the interior point stuff.
So do you need convex in both x and y, or was it for every y?
X, right? Okay. So like I'm only writing down the KKT conditions with respect to x, right? And that's all I care about. So if it's convex in x, I can always treat it like that. That implicit function theorem trick like always works. It's a well-posed convex problem, which it is in almost all these cases, right? There's some details there that no one asked me about today, but so like the maximum dissipation one explicitly is a second order Cohen program. The least action problem, usually someone bugs me about this. No one here. So I called it least action very deliberately. And usually someone's being pedantic and says, oh, stationary action, right? It's not really a minimizer. And this is where we get into a fight because it actually is a local minimizer. It's a local minimizer under a few mild conditions. In practice, it's always a strong minimizer. It's not actually a stationary point. It's a strong local minimizer if the time steps are short. And this is very, very easy to show because in the limit of small time steps, the Hessian of that problem is mass matrix. The mass matrix is guaranteed to be positive definite. So it is as long as your time steps are reasonable, is like locally complex basically. And yeah, so that one's benign also. So most of the problems, and the collision checking problem is convex, right? So most of these are actually on their own very benign, very easy to solve with interior point method. A lot of structure I can exploit, right? Whereas if I stack it all as an impact, it's a mess and there's no structure, right? Matt had the question online.
Let's see if I guess the
Can we
question.
hear Matt?
I probably need to unmute first.
Can you hear me? Hello?
We can hear you.
Okay, good. Yeah, so while we're on this topic, so classically when you compose optimization problems, you get essentially a higher order optimization problem, and it's typically stiffer. So numerical stability becomes more of an issue. Like combine linear programs, you get a QP. So are you finding you needed to soften the barrier function to get them to optimize well?
So yeah, I would say like these are still really hard problems to be clear, right? But so especially in these kind of like local tracking kind of contexts, like what we're doing in PC and we're warm starting, we're able to solve these really reliably to tight tolerances. So it's not so much that they're like we definitely start with pretty relaxed barrier parameters, but we're able to crank them down. So it's a matter of like, if you're kind of in the ballpark of a solution, the local convergence is very good. Like you get local superlinear convergence when you stack all this stuff up. It's when you're far away from a solution that life is very bad. And like the globalization is hard. So yeah, I would definitely say they're still really hard non-convex problems, but here at least there's like a recipe for getting fast, like very good local convergence, right? And at least in the simulation context, you're always warm starting. The time steps are always kind of pretty tight. I think like it depends what you're doing. If you're trying to do simulation, life is good. If you're trying to do local tracking kind of MPC, life is pretty good. If you're trying to do motion planning, starting from scratch without a good warm start, it's terrible. Forget it, right? So I think that's just kind of
That's why you have the MPPI. Do the MPPI, then you get the seed, and then you
Yeah.
optimize about.
or whatever, right? Like whatever you have.
Yeah, but even
You
a simple method like that is
Yeah.
enough to give you
Maybe.
a good initial guess, and then
Yeah.
you can just
So
optimize
yeah,
about.
this is the issue, right? It's the initial guess problem for the global planning problem is terrible. But yeah, if you're close, this converges really robustly, I would say.
Okay, that sounds in accord with the experience.
So, so my question is, as you know, there are certain mechanical systems that can cause paradoxes. you know,
Oh yeah,
sort of
like
causal
the Penrose
thinking, right?
paradox.
Yeah. And so, I mean, I've always thought that those are fundamentally due to causal thinking.
Yes. Yeah.
So my question is, if we pose, the large mechanical system model as an optimization problem, then we are in some sense not falling into the causality.
Yeah. This is
And so yeah, I'm curious, have you played with any of these,
Yeah.
mechanical systems to see if they produce?
So I thought about this. So here's a fun, like weird nugget. Rigid body dynamics with contact is not causal.
Right.
Yeah.
Right.
So I mean, that's where a lot of it comes from. So if you soften the contact,
But the way we solve it is
not this.
we classically
Yeah,
employ causal
Agreed,
thinking,
yes.
which results in the paradox.
Yes, 100%. Yeah. So I totally agree with this. If you do, so this is a really, really important point that I think is subtle and maybe, so the stuff we're doing here is all non-causal. Like we're doing effectively implicit integration here. So when you do this impact stuff, we're solving a root finding problem, but we're actually looking forward into the future, sort of jointly solving this thing, and the future and the past are all kind of tied up in a weird way. And it's non-causal. If you, and that's at the heart of why we can solve this nicely and why the numerics are good. If you take a purely causal, like, approach to the physics simulation, where you're using like an explicit Runge-Kutta method, say, you get horrible stiffness kind of issues, and it blows up on you. So yeah, this is a really deep kind of subtle thing.
Yeah.
I'm glad you brought this up. Yeah, this is a cool. Okay. So you can simulate those like Penn-LaVey kind of things.
Yeah.
With these methods.
And jamming and things.
Yeah. It's cool.
I think we need to finish now.
Thank you guys for